to that. Next one is going to be application of the X-ray radiograph, particularly widely used for the bone fracture, arthritis, any kind of the degeneration of the bones. You can able to visualize at the primary level. Osteoporosis, it is nothing but the type of disease where the bone density decreases. You can able to do a qualitative osteoporosis study, may not be quantitative. So breast cancer detection, that is using mammography. That is, as I said, swallowed items. Okay, particularly using fluoroscopy and other things, and particularly many times the kids and other things they swallow, and you can able to find out there is any hard items the children have swallowed, that you can able to screen it. The digestive tract problems, particularly as I said, any problem in the drinking or consuming the food, and also the certain lung diseases, asthma at the early stages and other things also can be diagnosed using the X-ray. Okay. So this is about the first and foremost imaging modality which has come in the medicine. Okay. Next, the limitations of the X-ray. What are the limitations? It gives 2D projection of the 3D structure. We cannot able to get the 3D information, and also we may not able to get the depth of information. Okay, what depth the particular tissue is exists, that information is not available, and also cannot differentiate between two soft tissue, because the contrast or the attenuation quotient of the two soft tissue is going to be same. Only it can able to differentiate between soft tissue and the hard tissue such as bone. Cannot measure the densities of the various tissue. So suppose you wanted to get a different images for the different tissues. At that time, density has to play important role. But here we cannot able to do that in the ordinary radiograph. Okay. So those are the limitations. So how to overcome this limitation? So that extension of that is itself is the computer tomography. Okay. So computed means using computer technology. Tomo means slice. Graphy means visualization. So what we are going to do is, so slice by slice, we are going to visualize the human body information. That is what is altogether computer tomography. So the concepts of CT I am going to explain with this particular simple sketch. So this is the banana, and I am going to give this banana to eat you. And before I'll give a caution that this banana has an insect, and you need to remove that insect and eat. Okay. So what is the best method you are going to do? You are going to remove the peel, and then what you do is you cut banana into 2 parts, and you find out whether the insect is visible. Then you cut into 4 parts, you check it, and you are keep on slicing the banana. Okay. So at one particular part of the slice, you may come to know where is the insect. Okay. So by which you can able to visualize that particular, and you can able to remove, and you can able to control. The concept is similar. The concept of CT is similar to this. But here we are going to cut physically. So physically we are cutting the banana and converting them to slice by slice. But in the computer tomography, we are going to the human body slice by imaginary lines using the X-ray. Okay, and that will be converted into slice by slice images. So, but by which you can able to visualize. Suppose there is a particular the abnormality in certain part of the tissue. By a mere X-ray, we may not able to find out where exactly the location of the abnormality. But using CT, when you take slice by slice information of the tissue, we can clearly come to know that which part of the tissue abnormality is going to exist. That is the concept. Okay. So what is the principle of CT? In CT, the structures of 2D object can be reconstructed from multiple projection of the slice. So what we do is in the X-ray, in the CT, so we use X-ray tube. So on the one side we have the X-ray tube, on the other side we have the set of detectors. So what we do is, so X-ray is going to go around the human body as it goes. Suppose it will make one complete circle, or it can be considered a half circle also. Okay. So what happens? The X-ray is going to penetrate through this part of the body. When it penetrates through this part of the tissue, and whatever the tissue which is present here, it will going to absorb the radiation. Unattenuated X-ray is going to fall on the detector. The detectors convert that information into an electrical signal that goes to the computer, where we have advanced algorithms, and using those particular algorithms, whatever the information coming from the detector will be processed, and we are going to reconstruct a particular image of that particular slice. Just 1 minute, my battery is getting off. Okay, sorry for the interruption. Okay, so this is how we are going to get a slice. This is one slice. So then if you move the X-ray tube to the little higher or lower, again you do the same procedure, you can able to generate the another slide. So the CT as such, it will going to provide the 2D information slice by slice. But using this 2D information, you can able to generate a 3D the image also. Okay, so this was developed initially by mathematically by the person, the scientist by name Radon in 1917. Then it is popularized by this particular technique after a long time in 1960s by Alan Cormack. And the first CT system was built in 1973 by Hansfield. So because of this particular, the development of the technology, the Cormack and the Hansfield received the Nobel Prize in 1979 for the development of the computer tomography. Okay. So one of the important concept of developing the image is the projection function. When an X-ray passes through an object, okay, based upon the thickness, based upon its density, what happens? The appropriate amount of the X-ray intensity is going to be absorbed. The X-ray is going to get attenuated, and that particular information with reference to the initial intensity and with reference to the absorbed intensity, we can able to find out how the intensity variation is going to be. So that can itself be. So this is the how the intensity of absorption or the intensity of the transmission is varying with reference to the object. Okay, so here the high intensity, since due to the object here low intensity. So this is the intensity profile. So if you convert that intensity profile, okay, so into a kind of with reference to the x and y coordinator. So that particular intensity profile itself is going to be called as a projection function that is given by f of phi. Okay, so this is from where to where, from source to detector. Okay, for a particular region. So this particular function is going to be called the projection function. This projection function is carries the information about this particular object. Okay. So what is suppose I have got one particular project function for an object. How I can able to reconstruct that particular image of that particular object? That is we call the reconstruction technique. So what we are going to get? So this is X-rays exposed from this one on the object. I'll get one projection function. If you pass through the other side, we may get another projection function. So from the multiple directions, what you do is, so we are going to expose an object for the different from the different sides. We are going to get the different amount of the intensity. So for example, from one direction we'll get one projection, from the other direction we are going to get the other projection. So if you are going to get all these projections from the different directions, and if you are going to back projection, we project them back. Okay, so this is the forward direction, so you project them back. So this is the direction of the back projection, this way, this way, this way. So what happens? All of them meet together, so at specific points. So when these back projection points are going to meet together at a specific points, so they generate an image based upon this particular projection function. Okay, so that is the how. There are the different algorithms for the image reconstruction. So one is called the back projection method, iteration method, 2D Fourier transform method, filtered back projection. Okay, these are the 4 popular techniques. I'll not go in detail. It takes a lot of time. So this is the iteration method. So we are going to expose the object at the different direction. This is the, assume that this is the initial, the attenuation. We need to, this is the actual image. This is the actual image, and these are the assume that this is the intensity, or this is the attenuation of this particular object. When we are going to reconstruct, we need to get this. So what we do is, we have this mu1, mu2, mu3, mu4. These are the values of that. So what we do is, we expose this object in the different directions. So that is P1, P2, P3, P4. In the iteration method, what we do is, this is the P1. So then we do P1 by P2, we'll get this one. Like this, we keep on doing iteration. So this is the fourth iteration. So which P1 plus P2 plus P3, P4. Then what we do is, we subtract 16 from this. Then we divide this particular from the 3. Then we will get this. So this is going to call the same. So this is our actual attenuation coefficient of this object. This is our image. Okay. So by which what happens, we can able to, by iteration method, we can able to reconstruct an image. This is called the back projection method. So you can see there are two objects. When you are going to back project on an imaginary plane, they are going to meet here to generate the image of this particular objects. Okay. So another very popular technique is going to call the filter back projection. So if you are going to do a back projection without filtering, at that time what you can see, so you can see this is a object is circular one. Okay, this is the object is the circular one. So we need to supposed to get, when we will back project of the different projection profiles, we supposed to get the image like this circular. But what happens? The image something like looks like a blur. Okay. So at that time, what we do is, we go for a convolution filter. That's called the filter back projection. So I apply the filter here. Okay, you can see here, this is the without filtering. So these are the functions which are going to filter. So they are going to cancel out the unwanted regions. And when you are going to reconstruct the image, what happens? We can able to get a perfect circular object of that circular image of that particular object. Okay, so in that way, so this is one of the very popular reconstruction technique, filter back projection, which is used in the CT. Okay, so these are the algorithms which is there in the computer system. When the information we get from the X-ray detector, they go to the system. That particular information is going to process using this particular algorithms to develop a CT image. Okay. So another important concept comes in the CT, that's called the CT number. So if you look here, this table, this is called the linear attenuation coefficient of bone is 0.38, water is 0.21, muscle, striated muscle or the skeletal muscle 0.20, fat, and the air is going to be 0. So there is very narrow difference in terms of linear attenuation coefficient. So using this linear attenuation coefficient, if you wanted to go for an imaging, at the time you may not able to get a very good contrast. So that's why what we do is, we express this linear attenuation coefficient equivalent to a certain number, which is going to be called the CT number. Okay. So in that one, so how the CT number is provided? Okay. So the CT number is provided with reference to the water as considered to be as a reference. So the water CT number is given as 0, and the object which is not going to attenuate at all, air. So whose attenuation, the CT number is given as -1000, and the hardest of the hardest, such as metals, they given as 1000, or the bone, it can be given approximately 1000 or near to thousands, around 808. So if you look here now, when you compare this particular column and this column, there is a large difference between these numbers. There is a narrow difference. When you are going to image the body parts using this the concepts of CT number, you can able to get a very clear cut contrast between the bone, fat, and the muscles. So that is how the CT number is going to be popularly used. Okay. Then comes to the CT machine. So this is how a CT machine looks like. So this is, we got the gantry. This is going to be patient table. So this is going to be completely automated system kind of things. Just by pressing through the computer itself, there we can able to operate this particular machines. Okay, so this is the inside of the CT machine. Okay, so one side we have the X-ray tube, and other side we have the other lot of accessories. What I am telling is very less. There is a many other accessories which are going to be used in the, but basic concept remaining same. Okay, So this is the how this animation looks like. Okay, so one side you have the X-ray tube, other side you have the detector. The X-ray tubes goes around the patient table. The patient remains still. Okay, X-ray tubes goes around to generate a slice of information. So every time what happens? So X-ray tube is going to move or the patient table is moved. Okay, any one. Okay. So this is how a conventional CT slices looks like. Okay, so these are abdominal part regions. Okay, so these are the abdominal region. So where you can see the clear cut the spinal cord. This is spinal cord. So this is spinal vertebra. So then you can see the liver part very clearly. Okay, so in that one, so slice by slice information you can able to keep on visualize. Okay, so any abnormalities and can be clearly observed using this CT. Okay, so that is the you can see. So these are in the abdominal region. Many of the tissues are soft, except you can see this is where I am pointing now. This is the vertebral column. Okay, this is vertebral column, vertebral bone. The vertebral bone is the hardest tissue. Okay, so that looks very bright. So remaining are almost like soft tissues. Okay, ನೀವು liver ತಗೋಬಹುದು, stomach region ತಗೋಬಹುದು, kidney parts ತಗೋಬಹುದು. They are almost like soft tissue. But among the soft tissue, there is the amount of the water which is going to present, the amount of the density is going to present is going to differ. Because of that, you will be able to get a contrast among the soft tissue also in the CT, which is not possible in the ordinary X-ray. Okay, right. So this is this animation going to give you clearly. This is the slice by slice information of the brain CT. Okay, you can able to see. So at different slices, you can able to visualize. Okay, so you will get slice by slice information. So the doctor is going to visualize all the slices one after the other, and you can able to find out which particular slice there is abnormality. So you can see in the left X-ray, you can see. So at this particular side, there is no abnormality. You can see now. You can see clearly it is going on. I'll show the abnormality where. Okay. So at one particular, see here, there is an abnormality. There is at one particular slice, there is an abnormality. So here also there is an abdominal the CT. So at certain part, the you cannot able to see the abnormality. So you can see, you can able to also get an information what is the size. You can see the size of the abnormalities varies from the slice. At one particular slice, the abnormality looks very bigger. Okay, so in that one we can able to get an information. When you reconstruct all together, when you are going to reconstruct all these particular slices, you can able to get a 3D out of which you can able to get what is the size of that particular abnormality. Okay, so that is the how this is a unique imaging modality that is very widely used to study the internal structure of the human body. Okay, so coming to the CT image characteristic, resolution matters. So how best you can able to differentiate two nearly objects. So jet sensitivity called slice thickness. So based upon the tissue which you are going to expose, so we are going to decide what is the slice thickness, whether it should be a 2 mm slice, whether it is going to 3 mm slice. Okay, so noise which is going to be generated, the contrast which you are going to get, and speed of the CT slide what you are going to get. So nowadays within less than a second we can able to get a slice information. Such level the technology has developed. Okay, so earlier when the first generation CT machines came, they used to take nearly 20 to 30 seconds to generate one slice of information. Nowadays, just by within a fraction of a second, we can able to get a slice of information. These are the CT image characters. Applications, injuries from the trauma. Suppose trauma agide, head injury agide, blood blockage agide. So that clearly you can able to see. Bone fractures, particularly compound fractures. So simple fracture you can able to visualize in X-ray, but multiple fracture, compound fractures, hairline fractures, which may not be seen in the ordinary X-ray, you can able to see in the CT. Tumors and the cancers in any part of the body, particularly in the brain, vascular disease. So any disease related to the vessels, heart disease, infections, and also used to guide the biopsies. Particularly, suppose you wanted to remove certain tissue for the biopsy, at the time, CT can also be used. And also when you come to that, again, there is a lot of scope to work in using CT images. Okay, particularly a better way of detecting the tumor, quantifying the the tumor sizes, tumor characteristics, and also the research also wide scope is available to find the stages of the tumor. Is it possible to find the stage of this tumor? All these are still open research problems which are going to be available for the research scholars. That is it. Next comes the digital radiography. So, what, as I said in the when I discussed about the detectors, okay, so you can use a radiographic film as a detector for the X-ray, but you can use scintillation detector, ionization detector, which convert the X-ray photon into some kind of electrical signal. So if the data is available in the electrical signal, as we know, faculty members, we can able to do wonders. We can able to process that data by converting that the analog data into digital and do wonderful processing of the data, by which you can able to extract more information and you can able to project better information. In that one, so the digital radiography has come with the advent of digital computer and the integrated circuit technology. So made image processing and data acquisition in digital format at a reasonable cost and within a short period of time. Okay, so what together are to digital radiography? Same film, procedure is same. Only thing is that instead of film, we use digital detectors. Okay, so once we will get this detectors, okay, so it is not digital detector. We get the detectors here. They convert the X-ray photon information into the analog current or the voltage that comes to here, that we convert that analog data into digital. So we'll get the digital information about the internal tissue information through this particular the analog signal that will be converted to the digital data that goes to the computer. We'll process that using suitable image processing algorithms. Then we'll get a digital image. So that digital image you can able to see on the monitor itself. Okay, by which nowadays majority of the doctors will go to visualize that digital image on their the CRT screens, and they can able to do the diagnosis, or you can able to print into on the film using a digital printer. Okay, again what you do is we convert that digital to the analog, and we can able to get an analog image. Okay, so this is an X-ray film. This is an X-ray image using taking by manual method using film. So this is a digital radiograph. You can see this is also chest radiography. So you can see the lot of contrast you can able to see. Okay, so because in the ordinary radiography you cannot able to process the image. What you can do, we are develop the film to get an image. But here we can able to process, we can able to get rid of noise, we can able to improve the contrast, by which you can able to see the better information. Okay, so that is the advancement in the field of digital radiography. So that is about the one of the imaging important modalities that's called the X-ray. Using X-ray, basic X-ray radiography, then fluoroscopy, computer tomography, then digital radiography. These are all. So as we know that X-rays are harmful. So when they are passed through the human body, there may be a certain kind of ionization. So if the body is exposed to the more and more X-rays, there may be a possibility that a normal tissue may become abnormal. So that's why, for a precaution point of view, most of the technicians and the doctors are going to wear a dosimeter that is going to provide you how much X-ray has been exposed on the body. Regularly, they need to check whether they are within the limitations. Okay. So to overcome in the certain, if at all possibilities are there, can we able to generate an image without using the radiations, X-ray radiation? That is nothing but the ultrasound imaging. Using ultrasound, we can able to develop. So I'll not going to read contents here. So when you pass a high frequency sound pulses onto the body, what they pass to the body at various level based upon the type of tissue. What happens? They get reflected back. That is what we call the echo. So what we do is we pass the ultrasound signal of high frequency, which may be in terms of megahertz. So what they do is they penetrate to the body. So what happens whenever the composition of the tissue changes, at various level, when the composition of the tissue changes, the ultrasound has a very good phenomenon that whenever the composition of any object changes or the tissue changes, at that particular the boundary, the ultrasound is get reflected back. So in that way, so at various level, the ultrasound will get reflected back from the human body. So in that once, what we do is we capture the echo. Reflected is nothing but the echo. Okay. Pratidhwani ಅಂತ ಹೇಳ್ತೀವಿ ಕನ್ನಡದ ಪ್ರತಿಧ್ವನಿ, that is nothing but the echo. So that reflected sound we are going to capture, that is nothing but the echo. So in that one we are going to whatever the reflected sound we are going to analyze by using the 2 to 3 information. One is at what speed the sound is coming back, at what speed it has been transmitted, at what speed it has come down, at what time I have transmitted, at what time I am returning the pulse. That's one. The time of each echo return, how much time each pulse has taken. Second, third one is amplitude of the echo signal. What is the intensity of the sound? What is the intensity of the sound which I have transmitted? What is the intensity which I am receiving? Okay. So once we collect this information, and what we do is using the computer systems, so we process this particular the data. Okay, so the distance data, intensity data, amplitude data will process that information itself can project it onto a screen which is going to appear in a 2-dimensional image. Okay, so that is the one. So this is how the concept comes here. So if I pass an ultrasound sensor, it is emitted here, it will going to hit the object, it will get reflected back. Okay, if I capture the reflected signal, I can able to find out at what is the based upon the at what time I transmitted the sound, at what time the sounds are reflected, by which I can able to find out what is the position of the object, how far it is from the sensor. Second one, what is the intensity of the reflected, based upon that I can able to characterize this object also. So this is the graph which is going to provide a very clear cut information. So this is the time x-axis, this is the voltage. So this is a transmitted pulse from a transducer. So from a ultrasound transducer I'm transmitting. So here this is the human body. Assume this is the human body. This is the skin surface. So whenever from the skin surface, what happens when it is going to interact here? So this is the first signal which will get reflected. This is the first echo what I am going to get. Then what happens? We have the different layers. From every layer we are going to get reflected pulse. Then suddenly there will be an organ. Assume that there is a heart tissue comes. There is an organ. So the composition of this organ is different from this particular tissue, and it's different from the skin. So what happens again? The more amount of the sound is get reflected. So like that, what happens? So every instant, okay, the sound is keep on reflecting back. So every instant I will find out with respect to time at what time the sound is getting reflected and what is the amount of the intensity. If I am going to get these two information, I can able to image this particular interior of the human body. And this is the one, the graph is going to provide you how the absorption of the ultrasound is going to vary for the different tissues based upon the frequency. Okay, you can see here. So based upon the frequency, the amount of the attenuation, ultrasonic absorption is going to vary. Okay, the bone is here, then brain, liver, kidney, muscle, they comes under the one group. Then the fat, red blood cells, water, and other things. So you can see in this particular the ultrasound absorption. Okay, so for the different wavelength is going to be differs. In that once, if I am going to pass an ultrasound to the different wavelengths, so we can able to generate a contrast images of the different parts of the tissue. That is how this particular ultrasound system is going to work out. So to generate the image of the ultrasound, so I'll make it clear. In the ultrasound, what we will do is we will have an ultrasound probe which generates ultrasound signals. Okay, which is going to be in terms of megahertz, which is not audible to the human perception. Okay, so they pass through the body. So once they pass through the body, from the body at various level, the sound signals are getting reflected back. Okay, meantime, when this ultrasound penetrates through the body, its intensity also get attenuated and it will get reflected back. So we capture these information about the reflected, at what time the sound is getting reflected back, and at what is the intensity of the reflected. So based upon that, we'll process that. So in that one, so there will be three modes of operation of the ultrasound system that we call the pulse ecosystem. We'll not pass the ultrasound continuously. We'll pass the ultrasound in the form of the pulses. Okay. So there is three modes. That's called the A mode, B mode, and BM mode. A mode is called the amplitude mode. B mode is called the brightness mode, and M is called the motion mode. Okay. So suppose what is the difference between A mode and A mode is going to provide the depth of information. Okay, if you go, I'll provide the more details in the next slide. A mode provides the depth of information. M mode provides with time. If an object is moving, it provides the motion information. B mode provides, so based upon the amount of the light, which is the sound which is being intensity sound which is reflected, I can able to generate image which provides a bright. Okay, so the B mode provides the brightness, M mode provides the motion information, A mode provides depth of information. Okay, in that. So in that one, so A or amplitude mode. So echo amplitude as a function of depth of penetration. So what the echo provides, the echo amplitude provides a function of the depth of penetration, at what depth a tissue is present. That particular information I can able to get. So this particular, this I already explained. For to understand in a simple way, so this is the ultrasound transducer. I am passing the sounds. So this is one tissue, this is second tissue, this is third tissue. So what happens? Ultrasound passes here, it get reflected. Okay, this is the first echo. Then, so certain amount, if this is going to be a certain extent, this is soft tissue, it will be penetrate this. Then it is going to fall on the second tissue. From this, now again composition changes. Again from this tissue, it will get reflected. So then it penetrates, passes, and falls on the third tissue. Okay, and it will get reflected back. So I'll get various steps. So this will be amplitude of the echo from 3. So by which I can able to get, so based upon at what time they are getting reflected, and with reference to this time, I can able to find out, so what is the depth, okay, at where is the position of that particular tissue, I can able to find out using the amplitude mode. Okay. So second one is B or brightness mode. So in B mode, the echo amplitude is used to modulate electron beam intensity. Okay, we use generally a CRT screen monitor. Okay, monitor is nothing but it carries a cathode tube. So what we do is, whatever the echo which is reflected back, the amplitude is connected to the electron beam of that is connected to the intensity. Okay, so that is nothing but the z-axis. So what happens? So in that one, so wherever the echo is coming, so we capture them. So we connect z-axis of the CRT. So what happens? Z-axis is related to the brightness. So whichever the part of the screen getting an appropriate current or the voltage, that particular screen becomes brighter. Okay. So in that one, just using this, I can able to explain you. You can see here, this is the same information. This is the same data now. Okay. This particular data I am getting converted to brightness. Okay. So what happens? This is nearer. This is the medium. This is going to be farther. So the nearer object looks very bright. So middle object is little gray color, and it looks darker. So I can able to find out based upon, I can able to make a particular object to visualize either a bright or moderately bright, or it is going to be the grayscale. Okay. So you can see here, this is a particular B mode display, how it comes. So this is if it is the amplitude of the image, for amplitude of the signal reflecting from the tissue. If it is going to be a pattern is like this, it will brightness will be something like this. Okay. If the tissue is something like it has a spread out, so I'll get the spread information like this. So if I take information like this, suppose this is the surface of the body, and this is a organ. Okay, what I do is I keep my probe on the surface of the body and pass the ultrasound. So what I can see on the CRT screen, I'll get first layer. You can see this is the first layer from the surface of skin. Then the second layer. So we after the skin again there is a reflection of this signal. So that is second amplitude, for which I will get one more line. So then there is a continuous soft tissue. There is no much reflection here. So between organ and this part, there is no reflection. So, but again, from when this organ comes here, from the surface of the organ, it gets reflected. So third amplitude. So on the other side of the organ, I will get the one more. So due to which, so this complete the object or the human body can be visualized in the form of a brightness spot. Okay, this is the how a B scan you can able to get it. Okay. So to get suppose if you use only one probe, only one transducer, you will get only one part of the tissue. Suppose I want a larger tissue to be covered. At the time we use linear array scanner. So this you can see, this is the n number of the transducer are used. They are going to be arranged in the form of an array. So we pass the array of the pulses. So you can see here. So we can able to get the larger tissue image on the screen. Okay, so you can see this is the fetus in the uterus. So this is the ultrasound image of the fetus, which is generated by the brightness mode using a linear array scanner. Okay. So this is the schematic diagram, how the block diagram is. You can see n number of the transducer going to use. So which is going to pass here, get it reflected. So simultaneously they'll connect it here. Ultimately they are going to be displayed. So here you can see we can able to get the fetus. Okay, so this is the fetus image using the linear scanner. You can see the lips, you can see the nose. So this is you can able to get interior of the also this is the part of the brain part of the fetus. That also you can able to see using the linear scanner using the brightness mode. Then comes motion mode. So particularly if you wanted to visualize the moving parts, as I said, a CT cannot able to provide a moving image, but ultrasound can able to provide. Okay. So what we do is here in the MO display, x-axis is driven very slow at a rate less than 1 sweep per second. Okay, where y-axis indicates the distance of the echo and x-axis indicates the time. So you can see here, this is the how. I'll just briefly explain. Assume that there is a pendulum which is moving in the water. So this is a transducer. When the pendulum comes here, okay, so a pendulum is nearer to the probe. At that time, what happens? I'll get an image here, which is near. When it moves far away, I'll get a spot. When I'll move again far away from the transducer, I'll get. So what happens with reference to time? So this object is moving. So what I'll generate a bright spots with respect to the time. Okay. In that one, I can able to visualize the movement of the object. Okay. So for which I use a RAM generator which is connected to the x-axis. Okay. So this is AMO display. You can see here. So this is the echocardiography, what we will call it as. Okay. So this is the heart image. You can see particularly these are the chambers of the heart. You can see clearly the heart walls which are closing and opening. Okay. So particularly on the this is the mitral valve and this is going to be on the right side. Okay. So clearly you can able to visualize the beating of the heart, the contracting, relaxation of the heart chambers, and the opening and closing of the valves. That is the so this is how the B mode along with the M mode is going to be provides you the visualization of the heart. So that is possible only in the ultrasound, may not be possible in the CT and other. Okay. So this is how we can able to visualize. This is still image. So this is the beating image. We can able to convert that. Further technology develop. We can able to convert into color Doppler. We call it as. Okay. So we can able to see incoming blood is going to be in terms of blue. That is going to be deoxygenated. The outgoing blood from the left ventricle, which is going to be a pure blood, which is going to be comes in the form of red. Okay, that way we can able to visualize using the ultrasound. Okay, so this is how animation provides. See what is the difference between A mode, B mode, and M mode. So A mode only the reflected echo. We can able to get the depth. B mode equivalent brightness. M mode along with brightness, I can able to get find the movement of the brightness. See, this particular object is moving. I can able to trace the movement of the object also. Okay, if the object is not moving, just I'll get a bright spot. Okay, this is the how A mode, B mode, M mode are used. Then comes the color Doppler flow imaging. Particularly, it is used to find the direction of the flow. Okay, this is the color Doppler imaging. So this is useful, particularly in certain places in the heart. Suppose the blood is flowing in the reverse. Okay, so particularly the blood has to move from atria to the ventricle. Okay, atria to ventricle. Suppose due to the certain one or the other regions, the blood is going to move back. At that time, what happens? The color Doppler image is going to help you. Okay, so this is the we can able to trace information. You can see the right side. So red one is going to provide the arterial blood flow. The blood flow in the arteries looks red, and the blood flow in the veins looks the bluer. Okay, so the veins is going to be deoxygenated. The artery is going to be oxygenated. So by which you can able to clearly see in the color Doppler which particular direction the blood is flowing. Suppose if at all there is a reverse flow. Okay, so suppose there is a blockage in the valve, heart valve blockage. Sorry, not blockage, opening. If there is an opening, there is a reverse flow. Okay, there is a reverse flow is going to happen. At that time, what happens? We can able to see in the color Doppler, is there any blockage is present in the heart. Okay, that is the extension of the normal ultrasound imaging. Okay, so coming to the applications. So ultrasound imaging, echocardiography. So for the movement of the heart and the heart valves, and also widely used to examine the fetus during the pregnancy and to monitor health developing baby. Once the pregnancy is confirmed, so after the nearly after 1 month, after 4 weeks or 6 weeks, the woman is undergoes scanning, by which so we can able to see the fetus development. Okay, continuously they need to monitor at different weeks, evaluate the blood flow, figure out the problems in the genital, particular prostate gland another problem to use to examine the lumps in the breast, thyroid glands, assess the joint inflammation and other. What are the shortcomings? Poor penetration through the bone and air. The ultrasound cannot able to penetrate through the bone, and it will get reflected from the air. So in that ones, we cannot able to get the imaging of the bone. We cannot able to image the lungs properly. Okay, so the quality depends upon the equipment and skill operator. So by where the probe is kept, based upon that image is going to form. Okay, image resolution is less compared to CT and MRI. The resolution is going to be poor because it is the sound signal will be getting reflected continuously. We are going to capture the intensity is not going to be quite distinguishable from one tissue to the other tissue. We may not able to get very clear distinguish soft tissue information. Okay. Next one is going to radionuclide image. So time is moving up. So I try to complete in another 10 minutes. So radionuclide imaging, nuclear medicine antare. So what is this altogether? So what we do in the nuclear medicine imaging? So we inject certain radioactive substances. Okay, when they are going to get injected into the radioactive substances, so any radioactive element has half-life. In the sense, they start disintegrating. So during the disintegration, they emit certain particles. That particle may be alpha particle, it may be beta particles, it may be gamma particles. Okay, in that way, so there are certain radioactive elements which are not harmful to the body, and their half-life period is very, very less. What we do is we inject such kind of the radioisotopes into the body. So after a certain period of time, they start disintegrate, they start emitting the radiation. So from where the radiation is coming, they are coming from the tissues. So they penetrate through the tissue and come out. What we do is we capture the radiations coming from the tissues, which are coming from the radioactive element, and gather that information and process that information. That processed information is going to be appears in the form of an image. That itself is going to call the nuclear image. Okay, nuclear medicine image. Okay, so how this particular imaging model is different. So that's how your body is functioning. Suppose you wanted to, you will not get the functioning of the the body organ or a tissue, but from the nuclear medicine imaging, you can able to come to know whether a particular tissue is functioning properly or not. So that's why X-ray, CT, MRI provides how a body looks like, how tissue looks like. Nuclear medicine provides how tissue works. There are two modalities. One is called the SPECT, single photon emission computer tomography. Another is called the positron emission tomography. These are widely technologies which are used. Okay. So generally, what we use in this SPECT radioisotope. So iodine 3 at 99 m, xenon 130. So these are all tracers of the radioisotopes. These are going to be used in the SPECT. Okay. So we inject them. So this is the SPECT imaging. So bodily through a particular injection medium, we inject the radioisotope. They go to the body, and which particular body you need to generate an image. So there we keep the camera. So the camera have the radiation detectors. They capture the radiation emitted coming from the body, and they get the data collection is the CT. So here the only difference from the here also it is called computer tomography. The only difference is we are passing the X-rays. They penetrate through the organ and come out and follow the detector. Here we inject a radioisotope. They go into the body. From the organs or the tissue, they start emitting the radiation. So these radiation will be penetrate through the tissue, through the organ, and come out of the body. When they come out of the body, we capture using the camera, which moves around the body. Okay, by which you can able to generate an image. So this is the SPECT scanner. This is how it looks like. We use a gamma camera. Generally, these all radioactive elements, they emit the gamma radiation. Okay, we use the gamma camera, high-end gamma camera. So the gamma camera using the computer. So the system will be connected to the computer. Again, we have the reconstruction algorithm. By using reconstruction algorithm, we develop the images. These are SPECT images. So here you can see the resolution is not very high quality, but information we are getting is high. So you can see we can able to generate a color information. So what it includes? So red includes high activity, yellow includes the little lesser. So dark blue includes no activity, like that. Okay, in that one, so we can able to get the functioning of a particular tissue. Okay, so you can see here the brain tumor. We can able to detect the brain tumor. So a tumor tissue has a different kind of functionality. Okay, so due to which the activities there is going to be high. It looks dark, the reddish, and also the yellowish. So it indicates clearly that this is the brain part. Okay, so the MRI is going to provide a contrast information about the brain tumor, but here a color image you can able to get. Okay, so Alzheimer's dementia, depression, you can able to get such kind of information by which you can able to get the information of the function. Okay, so another is for the PET imaging, particularly when use the radioisotopes such as 11C, 13N, and 18F. These are all the isotopes. So when they are going to be injected, they generate a positron. All of you know about the positron. They disintegrate into two generate two gamma radiation. So which are going to move in the opposite direction. Okay. So when they are going to be injected, so they go to the certain part of the tissue. They start emitting the gamma radiation. So surrounding that particular tissue, we have the scanner, which has the detectors. The same thing. So there, that is single the positron. Single here is positron emission tomography. Okay. So that is the only difference between SPECT and the PECT. Okay. Again, we will capture the radiations coming from the tissue. So these particular radiations will be gathered, processed using the algorithm, and they're going to be displayed on the monitor. Okay. So this is same concept here. This is PET scan. This is the how PET scan is taking place. So how you can able to differentiate? You can see this is normal PET image of the brain. So mild cognitive impairment. So cognitive impairment is there. Certain learning disability may be there. So certain perception may be problem. Okay. So at that time you can see this is normal activity of the brain. This is certain abnormal activity. There is a cognitive impairment is there in this particular the brain image. Alzheimer's disease. In the Alzheimer's disease, a lot of the neurons are going to die. Nerve cells are going to die because of the information is lost. At that time, you can see this kind of image. The functional aspect you can able to get from the PET images. Okay, that is the unique nature. So this is the healthy control. This is the Alzheimer's disease. Okay, so we can able to get the various functionalities of the different activity. So suppose hearing activity you wanted to analyze, vision activity you want to analyze, learning activity you analyze. You can able to use the SPECT image. Okay, that is the so the nuclear medicine is going to provide you functionality. The next one is going to be MRI. So magnetic resonance imaging. You use magnetic principle here. Okay. So we have the water in the body. So in that one, so we have a nucleus. In that one, we have the protons, the positively charged body. When you consider under normal condition, all these particular particles are randomly aligned. Okay. So the net magnetization here is going to be 0. But when you are going to pass a magnetic field, certain atoms are going to align in the direction, certain they are going to align in the opposite direction. That creates a net magnetic field in one particular direction. Then what we do is we apply a radio frequency field, so by which we tilt the magnetic field by 90 degree. Okay, so what they do, they absorb a radio frequency. So and immediately we remove the radio frequency. So afterwards, what happens? They get back to the original direction. While coming to the original direction, they emit the signal that itself is going to be called the pre-induction DC signal. When you capture the FID signal, we can able to generate the image. So this is the how it will. First step. So what we do is we pass a magnetic field. So the hydrogen is going to get aligned, the proteins get aligned. Then what we do is we put an RF excitation, so which will be up 90 degree. So what happens? It will go to flip. Magnetic field is going to flip. So immediately we remove this RF field, due to which what happens? It is going to come back to the original direction. This is called the relaxation time. During this process, it will emit the signal. That signal is going to call the free induction decay signal. That signal carry the information about the signal which is coming from the particular tissue. Okay. So this is the particular process. You can able to see the animation 180 degree out of phase. Then what happens once you remove the pulse, we will get an echo. Okay, that free induction decay signal comes, which you are going to process. Okay, so this is the MRI system. Okay, this is the how the MRI images looks like. Okay, so you can see the various slices of the MRI we can able to visualize. Okay, so when you compare CT and the MRI can able to provide a better resolution of the soft tissues. Okay, CT provides very good contrast among the hard tissue and the soft tissue. The contrast or the resolution among the soft tissue in the CT may not be very, very good, but the contrast what you get among the soft tissue is extremely good in the case of the MRI. Okay, that is the thing. Okay. So this is you can able to get the various slice information of the various position. If scanning will takes place in one particular direction, but you can able to generate the visualization from the different directions. Okay. So medical thermography by using the human body is a hot object. So our body temperature is under ideal condition is 37.2 degrees Celsius. So any hot object, as you know, that emit radiation. The human body emit IR radiations. So this IR radiation, if you are going to capture using these thermal detectors and process it, you can able to generate an image. That itself is called the thermal imaging. The lot of the scope is there for the research in the thermal imaging. Okay, so here which particular part of the body is more active, which particular part of the body is less active. But thermography, you can able to image various parts of the body. Okay, various parts of the body. So that indicates which part of the body is active, which part of the body is generating heat. Suppose if I am going to rub my hand, my palm, the heat is generated. At that time, this particular part of the palm, if I am going to image, it looks reddish. Okay, other part looks bluish. So where there is not much activity, where there is no heat generation. So that particular looks like bluish in nature. Where there is lot of activity or where there is an abnormal tissue. In the abnormal tissue ದಲ್ಲಿ ಏನಾಗುತ್ತೆ activity ಜಾಸ್ತಿ ಇರುತ್ತೆ, cell multiplication ಆಗ್ತಾ ಇರುತ್ತೆ, that will be part will be active, there heat will be generated. So when you are going to image human body, if there is an abnormal activity, that particular part also looks like reddish in nature. Okay, so in that one, so this is a lot of scope is there to work on. It is not still widely used for diagnostic purpose. A lot of research is going on. So electrical impedance tomography, so human body is conductive. If you use the what is the conductivity, permittivity, the impedance of the part, you can able to generate the image. So what you can do is you can mount the electrodes. So at various points, what is the conductivity you can able to get, so that you can able to gather the information and develop an image. That is called the so electrical impedance tomography. Here also you can able to get this slice information. Here we are mounted at this particular position at the chest region. When I'll mount, so throughout this I'll mount such some 10 to 20 part of the body. So I'll get slice information this part of the body. If I mount above here where I'm pointing now, I'll get slice of information here. Okay, so like that. So this is also research is going on. So particularly when the babies, infants, they are not able to cooperate for CT and MRI and other things, we can able to get the information from the infants. Okay, other imaging techniques, image based procedure, angiography, angioplasty. Particularly if there is a blockage in the vessels, we go for angiography. Angioplasty is to treat that particular blockage, balloon angioplasty effective. So or putting the stent. Okay, optical coherence tomography, particularly it is widely used, particular to image the retina, various layers of the retina. Retinal damages can be viewed using OCT. Laser based imaging, photonics is also coming up. Fusion imaging. As I said, CT provides very good contrast for the hard tissues and the soft tissue. MRI provides very good contrast among this soft tissue. In that one, if you club CT and MRI, you will get very good information. So that's for the fusion imaging. In that direction, you can able to club PET with CT. So PET provides functionality of the tissue. CT provides good anatomical structure. So by which you can get anatomical structure, functionality. Similarly, you can able to club PET with MRI. Okay. Then you can able to use imaging for surgery. That's for the image guided surgery. So we use certain amount of the imaging for the gamma knife surgery to treat the particular tumors in the. Another is for the robotic assisted surgery. So nowadays you have heard robots itself you do this surgery with high level of precision. Okay, but for to guide the robot we require image. Okay, so in that one, so that is called the robotic assisted surgery or the image guided surgery we use. Okay, so this is angiography. You can see very beautiful image of the brain vessels. Okay, so this is OCT, optical coherence tomography. This is layer information of the retina. You can see the various layers of the retina. So if the retinal damages the image in OCT, this is laser imaging of the vessels, and this is the fusion image. CT, this is CT, this is MRI. When you club here, you can able to get a better information. So this is image guided surgery by you looking at the images coming on the screen. Okay, the doctor is going to perform the surgery. Now it is become a routine procedure. Most of the surgeons, they use image guided surgery, and this is the gamma knife surgery. Using the gamma radiation, you can able to treat a tumor or cancer tissue in the brain. Okay, so in this way, the lot of the imaging the many imaging modalities are used for various procedures. Okay, so that's why, as I said, one imaging modality may not be helpful to get characteristics of a human body or human organs or a tissue. So we require different imaging modalities for the different situation. As I said, if you want a good contrast of the soft tissue, go for MRI. If you want a good contrast of the hard tissue and the soft tissue, go for CT. Okay, you want the information of the functionality, go for PET or SPECT. But you want to visualize the movements of the tissues, go for the ultrasound, like that. Okay, so in that, but there are certain challenges in front of the engineers that we need to look, we need to focus. So what is that? How to get high quality images? Okay, so certain images, lot of the image processing techniques are we are coming out. New algorithms were coming to improve the quality of images that is still existing. One of the just at this particular moment, I wish to tell you. Suppose you can able to work to improve the quality of the ultrasound images. As I said, the resolution of the ultrasound images is very poor, but you can able to work out how to improve the quality of the images what you get from the ultrasound. Okay, how to get high quality information from the processing and analyzing the images. Okay, so this is high quality images, high quality information, not only just image. So what information I am able to get? So nowadays what we do is we call it a, when you do any digital image processing, we call it the feature extraction. So how best I can able to use these images to get best information, that is also challenge. Based upon that, I can able to analyze that particular. Once I get the features, I can able to analyze that particular image, whether it is a normal image, whether it is an abnormal image. I can able to find out what stage of the abnormality, then which parameter contribute for the disease diagnosis and treatment. Okay, so when I extract the features, there is n number of features I may get, but which one may be good to diagnose the disease? That is also a challenge. So particular medical images are subjected to the lot of variations based upon the illumination, based upon the type of the machine which you are going to use. There are certain limitations, so there is certain inconsistency. That also we need to standard. Okay, images may have the poor resolution, which makes the lesion detection and diagnosis difficult. If the resolution is poor, you may not able to diagnose, or you can never differentiate the normal tissue with the abnormal tissue. So clinical images may contain reflections and the shadows. So sometimes, so based upon the which direction the radiation goes, which direction ultrasound goes, from where you are going to capture the data, there may be reflection data, there may be shadow data, which you need to separate out to in order to get the correct information of the tissue and to diagnose properly and to differentiate from the reflection data, shadow data from the lesion data. Okay, so these are the variety of challenges are there in front of that. In that one, the faculty members, research scholars, they can focus on these particular challenges by which you can able. Along with this, so you can use the AI tool, so by which you can able to develop and automated the diagnostic techniques, which is very essential for the physicians, doctors, radiologists. Okay, so this is what I want to tell about. So about the medical imaging modalities. With this, I am concluding my talk. This is where I am working. So University of BDT College of Engineering, Davangere. So thank you, one and all. If there are any questions, I can ready to answer one or two questions.
So participants, with if you have any questions, queries, please.
Shall I stop sharing now?
Yes, sir.
Okay, I'll stop sharing now.
Yes, sir.
Right, yeah.
So, thank you, sir. We have given a wonderful information on image processing and CT signal processing. We are given a wonderful. We are already seen from beginning to till time. So you have seen the complete information and knowledge, technology, how it changes, how we have to update. Very useful to our faculties and as well as research scholars and other ACT faculty college members also. Thank you, sir. Very great, wonderful informations.
Hey, if any participant has any questions, already time is late. You can leave your question with coordinators. So they'll pass on the questions to me. I'll get back to you whenever the time permits. Once again, I thank Professor Siddesh and Department of E&C, SCMIT Chitradurga, giving me an opportunity to share a few of my thoughts and the knowledge in this particular area. Once again, I congratulate and wish all the best for all the participants for a successful completion towards this particular FDP. Definitely, this FDP will provide you a lot of information for your academics and research. Thank you, Ananda.
Thank you, sir. Very grateful. Thank you, sir.
Dear participants, we will share the feedback link for this session right now in the chat box. Please fill the feedback form and attendance is compulsory for your certificate. Thank you. Next session will start by 2:15. We'll share the link, and next session will start at 2:30 exactly. And for the participation, 100 participants are allowed in the Zoom platform, and we also share the YouTube streaming. So we'll also share the YouTube link for viewing the entire sessions. Thank you. Just within 2 minutes, I'll share you the feedback link. Dr. Ganesh. ಚೆನ್ನಾಗೈತೆ ಫಸ್ಟ್ ಟೈಮ್ ಯೂಟ್ಯೂಬ್ ಲಿಂಕ್ ಎಲ್ಲ ಕೊಟ್ಟಿದ್ದೀನಿ.